Hi, thank you for joining me on this presentation on our ongoing research project at Heriot-Watt University regarding the coupled adsorption and precipitation modeling of scale inhibitor squeeze treatments. I'm Mahdi Kalantari, and this research project is supervised by Dr. Vasquez, Professor McCoy, and Professor Sorby. Inorganic scales are one of the big problems in oil and gas industry. They can be occurred in the formation and cause the formation damage, or they can be occurred in the wells and other production facilities and can reduce their efficiency or completely block them. By the way, in all cases, they can cause the loss of the production for us. And at the same time, the remediation of these problems are very, very expensive. So it's more intended to prevent the scales to build up rather than remediation of the scales. One of the most widely used treatments for prevention of the scales to build up in the formation or production facilities are using the scale inhibitors. Scale inhibitors are some chemical agents that can be squeezed into the formation or can be injected in the production facilities. And these chemical agents can bound to the ions that are the building block of the scales and remove them from the solution. And by this way, inhibit the scale problem. Scale inhibitors can be squeezed into the formations and they can be retained in the formation during the injection phase. And after that, they can be released to the production stream during the production phase and maintain some level of the concentration of the scale inhibitors in the production stream for a longer time to prevent the scales to be built up in the production facilities and the formation. So the scale inhibitor concentration in the production stream will be decreased through the time, and the scale inhibitor squeeze treatment will be efficient until the scale inhibitor concentration in the production stream drops below a certain value, center concentration value called MIC, minimum inhibitor concentration, which is a unique concentration for each combination of the scale inhibitor formation condition. So the scale inhibitor squeeze treatment need to be conducted on a repetitive scheme, for example, every 6 months. And this period of time is called the squeeze lifetime. This squeeze lifetime is determined usually by the simulations in the industry. But unfortunately, currently the simulations are not comprehensive. In other words, they are not considering the detailed mechanisms that are occurred in the scale inhibitor interactions with the formation one. Scale inhibitors are usually retained in the formation through the two different schemes, two different mechanisms. The first one, which is very well known, are the adsorption mechanism, in which the scale inhibitor molecules are adsorbed to the surface of the rocks in the formation, and they will be dissolved to the solution as the scale inhibitor concentration in the solution decrease. The other mechanism is the precipitation one, which is usually occurred in the reactive formations like carbonates, in which an acceptable level of the divalent cations exists. In the precipitation mechanism, the scale inhibitor molecules are coupled and bound to the divalent cations like calcium and magnesium, and will be precipitated in the formation, and later as the scale inhibitor concentration decreased in the solution, they will be redissolved in the solution, and the bound between the scale inhibitor and calcium or magnesium will be break, and the free scale inhibitor will be released to the solution, and that can hold the scale inhibitor concentration on some levels upper than the MIC values. So the focus of this research is on the modeling of the coupled adsorption precipitation actions of the scale inhibitor molecules. We know that the coupled adsorption and precipitation consideration can enhance the modeling accuracy and enhance the efficiency of the squeeze treatment designs. And by that way, it can save the time and, more importantly, money for the operators or the service companies that are operating the scale inhibitor squeeze treatments. Okay, coming to do the coupled modeling of the scale inhibitor squeeze treatments. First, we need to develop a coupled equilibrium model for the adsorption and precipitation of a scale inhibitor, in which we are considering a system of the scale inhibitor, a brine, a carbonate, and we are doing the equilibrium in this system. For modeling this system, we need to first consider an equilibrium model without any adsorption and precipitation. For considering the equilibrium model, we need to consider all the reactions that are occurring in the system between the engaging species. These reactions are all the carbonic system reactions, carbonate dissolution reactions, scale inhibitor dissociation, and scale inhibitor complexation reactions with the calcium and magnesium. Please note that the scale inhibitor dissociation reactions are variable. The number of these reactions are variable and dependent on the protonation capacity of the scale inhibitors, because scale inhibitors are modeled as the weak polyacid in this system that can be protonated to some degree and coupled to the calcium and magnesium ones. So when we are talking regarding the species in this system, we are talking on the, for example, nearly 44 species for the case of DTPMP calcite brine system. Then we are considering all these reactions in conjunction with their reaction constants, with the mass balances of the key species in the system and the charge balances. And by combining all of these reactions and balances, we will end up to a nonlinear, to a set of nonlinear equations that can be solved by the numerical methods. And the result of the numerical method would be the concentration of some key components, key species, that the concentration of other species can be calculated based on the values of these key species concentrations. And by calculating the concentration of all species in the system, the whole equilibrium will be characterized. Then we need to go through the adsorption bit. In the adsorption part, the amount of the scale inhibitor that is adsorbed to the scale to the rock surfaces will be calculated and removed from the solution, from the result of the equilibrium model. For modeling the adsorption part, we have different methodologies, different models, which is usually called the adsorption isotherms, which some of them are very well known and widely used, like Langmuir or Brownlee or something like that. And they can calculate the amount of the adsorbed scale inhibitor or other species based on their concentration in the solution. So using the adsorption isotherms, we can calculate the amount of the adsorbed scale inhibitor to the rock surfaces. And by calculating the amount of the adsorbed scale inhibitors to the rock surfaces, we can remove the scale inhibitor based on these values from the whole spectrum of the species containing scale inhibitor, with considering their stoichiometry. After that, we need to calculate the amount of the precipitation ones. For the precipitation part, one, we have the initial concentration of the scale inhibitor in the solution resulted from the equilibrium model, the amount of the adsorption resulted from the adsorption modelings, and the final solubility of the scale inhibitor in the system, which is specific for each system and has been inputted into the model. And based on these three values, we can calculate the amount of the precipitation. And based on this value, we can remove the scale inhibitor from the whole spectrum of the complex scale inhibitor with the calcium and magnesium. So the precipitation will be removed from the scale inhibitor complexes only. Now we have the coupled equilibrium model, and we need to couple this compressive model, equilibrium model, to the transport model, because we are going to use this model for the scale inhibitor squeeze treatments. For the transport model, we are considering the advection diffusion equation first and calculating the concentration of each species in the system for each cell at each time step. And at the end of each time step, we are inputting all of the concentrations into the equilibrium model here. And based on the equilibrium model, we are calculating the result of the model for the in solution concentration of a species, adsorption concentration of the species, and precipitation concentration of the species for each cell. And based on these values, we can update the concentrations in each cell that can be used for, with the transport model for the next time step. After the modeling of the process, we need to confirm and validate the model. For the equilibrium model, first we need to check the basic cases, basic well-known cases like carbonic system distribution of the species or scale inhibitor dissociations systems, and check the results with the literature reported values, which has been done up to now. And also, then we need to consider the previous and new experiments regarding the DTPMP system, calcite, and brine system, North Sea seawater. And the result of this equilibrium system will be checked with the results from the model to confirm and validate the model. And it has been done up to now, and we have got very good results for these systems, and nearly we have confirmed our developed model for the equilibrium part. And later, by coupling the equilibrium model with the transport model, we are going to validate the coupled model, coupled transport model with the core flood experiments, and later, the end of the project, we'll validate the model with the field, real field squeeze treatment cases. Finally, I need to appreciate the support from the Energi Simulation and all other sponsors of this research. If you are interested in more details of this research, you are more than welcome to contact us. Thank you for your attention.